In this video, we're going to look at the importance of visualizing data when trying to understand the form it has. And it's important to look at data as well as calculating statistical measures of it. A very good example of why it's important to do this is the so-called Anscombe's Quartet. You can find the data given on a Wikipedia page for Anscombe's Quartet, which I've highlighted here. And the data is as follows, and we're going to look at this using Mathematica. So you can see there are 4 data sets, a series of x and y values that go together. So that's the first data set, the second data set, the third data set, and the fourth data set. And you can see at first glance they look, broadly speaking, similar. I have some x values that have similar sorts of ranges. They range in x values from, say, 5 to 10 in most cases. They have a range of y values. The only possible discrepancy is perhaps that these x values for the fourth data set all happen to be quite similar to each other apart from one value. So we can define those variables as we by highlighting this cell and hitting the enter button or shift return in Mathematica. I can also define all the data all at once, where I've taken the 2 vectors for the first data set, grouped them into a list, and I've transposed them so that they now appear as XY pairs. So I just define that as well. And to show what that data looks like, I can tabulate it using this function table form. And you can see that, again, the data looks more or less okay. So let's look at the statistical properties of each of those 4 data sets. So firstly, I can calculate the means of all the x values. So each of those 4 x vectors has the same average value, which is 9. And if I scroll down a little, you can see that the variances are also the same. They have the value of 11. Okay, so you can see that this mean function, I'm applying it to each and every member of this list, where each member of that list is one of those vectors. So the mean of the x values and the variance of the x values are all the same as each other. That's also true for the mean and variance of the y arrays. The mean is about 7.5 and the variance is 4.12 or so, so they're very, very similar. And we can calculate the correlation between the data sets. So I've taken all those data sets, which are the x, y values, I grab them one at a time, and then I look at the correlation to see how those x, y values vary with each other, to see whether there's a good correlation between them or a poor correlation. And we see that the correlation values are also very similar, they're about 0.816. And indeed, if I do a line of best fit for those data sets, you can see I do a linear fit, which is, I highlight here, I do a linear fit for each of the data sets, and I calculate what equation that is as a function of x. And you can see that for all 4 data sets, they have the same correlation, they have the same intercept, which is about 3, the same gradient. So for all 4 data sets, the best fit line is y equals 0.5x plus 3, almost exactly the same. Just press enter to see that. So if I do a numerical calculation of all these 4 data sets, there's no simple calculation which tells me that the data sets are different to each other. Now obviously there's a clue here, so let's scroll down. What we're going to do is we're now going to visualize that data. So I take those lines of best fit, which I've calculated before, and I create a plot of those fitted lines. So I take the linear model fit of the data here, and I turn it into a function where I plot those values from x from 2 to 20. And then I plot the data. Obviously, there's going to be a big reveal in just a few seconds. So I generate those two data sets. So those 4 plots for each of the 4 data sets. And now what I do is I plot the best fit line with each of the 4 data sets. And hey presto. So you can see that those 4 data sets are all very obviously different from each other. Let's look at the one on the top left. This one looks like a fairly normal sort of data set. We have some kind of fluctuation of the y values around some average behavior, which is given by the fitted blue line, and that sort of looks okay. Now, without having visualized the data, we would have thought that the bottom left data set would have been equivalent in all ways. But clearly there's a problem. The problem is that this y value here, for this particular value x, which in this case is about 13 or so, this is clearly telling me that there's a problem with this data point. At least we think there's probably a problem with that data point. And really this data point should be eliminated and the true gradient should be different, and the correlation of these points, the correlation coefficient, should also be much higher than for this data set on the top left. Now the data set on the top right is different again. We can see that this data set, there is clearly some higher order behavior. Now we can only justify that that's the case if we had an error bar for each of these data points, which were to give us a large chi-squared value for our blue fitted line here. But nevertheless, that even without those error bars, there's a pretty strong indication, isn't there, that this data on the top right has a radically different form from the data, the other two sets of data that we've seen. And of course, the bottom right is even worse. You can see that this shows us that actually the majority of the data points, there is no proper correlation between the x and the y values. I can have the same x value and a variety of y values, and the linear fit, the means and variances are all created by a single data point out here in the wings. So this just shows an example of why it's important to look at your data as well as calculate statistical measures of that data. And if we think back to generating points on a sphere and wondering if those points are uniformly distributed or not, there's, whilst we can do statistical measures of those points to see if they're uniform, nothing beats looking at things by eye first to see whether everything is as it should be. So visualizing data is very important.